Hi, today I'm going to introduce you to standard deviation and how it relates to the distribution of your data. And we're going to sneak into z-scores to help you get into those modules. So right off the bat we have xi, or a bunch of xi's. If you remember, xi means each x. Now this data set, let's pretend that it's average speed in a bike race. There's a 50-mile bike race, 20 people, and at the end we find everybody's average speed and we record it here. So average speed in a bike race. But now we're going to change it back to xi, and you'll see why in a second. Okay. So these are average speeds, and we want to find the standard deviation. Do you remember the very first thing we should do is to find the mean? So here we're going to call it x bar, and we're going to write out bar for the sake of ease of not going into symbols and equation editors. So we have x bar, which is the mean. That's your second column when you're looking for standard deviation. Now, to find the mean, we add all of these up, so you probably remember. Then we divide by the total number of observations. In this case, it's 20. And we have 22.25. So that's our x bar. Now this is why I changed this back to xi, because here we're interested in each and every single observation, each and every single x. For x bar, the x bar column, we're interested in the x bar, the only mean of the data set. And that mean is 22.5. So, I'm sorry, 22.25. So here we fill out 22.25 in each and every single cell. We're not interested in xi, each and every single x. We're just interested in the x bar, the mean, the one and only mean in this data set, at least. So the third column, do you remember what it is when you're computing standard deviation? We need to get the differences. That's the whole purpose of standard deviation, is to figure out how far everything is from the mean, how much does it deviate from the mean on average, and really that's exactly what is going on when we compute standard deviation. We're taking the difference, and we're finding an average with a twist, and I'll get to that in a second. So this column is xi minus x bar. We want to take every x, subtract it from the mean. So we take 14 minus 22.25 and we get 8.25. We carry this all the way down with some Excel magic. And the next thing we want to do, if you forget, what you can do is just sum this column and you'll remember. Because it turns out if you sum this column, you get 0. So it looks like the average distance from the mean is 0. And if you go back to our lesson about averages and balancing that seesaw, you may realize why. The mean is trying to balance the weight that's on one side with the weight that's on the other side. So that's exactly what's happening here. You have as much negative weight here as you have positive weight here, and it's zeroing it out. So it's kind of like telling you the mean's right in the center. Everything's balanced. There's as much weight on one side as the other. So here's why we square everything. If you remember this step, we need to take, let's call xi minus x bar the difference. So let's call this the difference squared. Okay, or squared differences. So we raise everything to the second power here. We drop it down. And now we can sum this up and we get a number, 755.75, and it's a non-zero number. So by squaring, we remove the negatives and we're just getting absolute value. An absolute value would theoretically be another way that you could do this, and that's for another time and place, but it's doing the same thing at squaring it. It's taking out those negative values. So we're just getting the total absolute differences without regard to direction. So at this point, we have what we call sum of squared differences, and that's 755.25. And now if you remember, at some point here we have variance, and then we get to standard deviation. So we're at the variance checkpoint. We're just about there. So what we do for variance is take the sum of squared differences and we average it. Remember, standard deviation and variance are a measure of average variance or difference from the mean. So what we do is we take 755.75, we divide by 20. Now again, some will say divide by 20 minus 1 or some other tweaks like this. It's very theoretical, very involved, and we're okay for right now to just divide by 20. I believe the book in some places says just divide by n, the total number of observations, and in some places divide by n minus 1. At this point, just divide by 20. You'll get the idea, and this is a recognized version of variance. So we now have variance at 37.78. And if you remember what standard deviation is, or I could say if you remember, variance is standard deviation squared. So we basically have standard deviation ready to go. We just need to take the square root of this, some Excel magic, and we have 6.147. So that's it. You have standard deviation. Now, let's lock in right there and sort of build on to something else now. Because this lesson is going to get you into standard deviation even more. We're going to start talking about z-scores. Now, the way you should think of this is, for every data set, you can do this thing that we just did. And what this does is tell you what the ruler is going to look like for this data set. And in this case, your ruler, your unit, is 6.15, if we round up, miles per hour. You should realize that standard deviation keeps the unit of measurement of your xi's here. So 6.15 miles per hour is the ruler for this data set. Now you might say, what ruler exactly is it? So if you come to this Math is Fun website, and I'll put this on our Blackboard site so that you can explore this a little bit, and it's in your lesson modules as well. What happens here is, this is called the standard normal distribution. That's this exact shape that you're looking at, and it has a few characteristics. It's bell-shaped just like this, but it's not too peaked, doesn't have too much kurtosis, and it's not skewed. Its skew is 0. And incidentally, its kurtosis is 3, but we'll talk about that later. So this is sort of the gold standard of distributions. Okay, we assume that data sets have this distribution in order to work some stats magic. And what happens here is, as you can see, at one standard deviation, remember that's our magical ruler, we have about 34.13% of cases are going to fall beneath that. You can see that this is the thickest part of the curve. So what it's doing is putting people's speeds, if we go back here, and graphing it out, 1 mile an hour, 2, 3, 4, 5, 6, up to 50. And what happens is, in a bike race, most people are between something like 18 and 24 miles an hour, something like that. So most people come in here. So the height of this is the number of people that fall at any given point. And as you can see, it's very dense here in the middle. So the message is clear out here past 3. There aren't very many people, okay, that average maybe faster than 34 miles an hour or something like that. And there aren't very many people here at -3 that average maybe less than 12 miles an hour or something like that in a bike race. So what happens is, average is very common, and as you get super fast, it gets less and less common, and as you get super slow, it's less and less common. And we talked last week about how there are certain things that tend to have this normal distribution. We're not going to get into that too much, but the key is that this 6.14 is our ruler in this data set, because that's the number that gives us the 34, let me get back to this, that gives us that 34.13% between 0 and 1. So if we take the average speed, that's 0, okay, 22.25 is going to be right here at 0. This is your mean right in the middle. Remember, we talked about that last week. Then, if we add 6 whatever our standard deviation is, 6.15 to the mean, so here let's do the mean plus the 6.15, we get 28.40. So this number right here is 28.40, and what that means is 34.13% of riders have a speed between the average 22.25 and this 28.40. So it's a little confusing to people at first, and it really takes calculus to understand all of this, but fortunately for you, in most cases, most people don't love the calculus in a stats class in the social department. So fortunately for you, what we're doing is just showing you a way that you can compute that through this method using this table. Okay, you'll get standard deviation, and this number will give you, you can think of it like magic unless you love calculus. Like magic, it will give you these percentages that you see in this table, with 34.13% up to here, and then a little bit less, 13% here, and less, and it'll thin out just perfectly and match this distribution. And that's it for this video. The next video is going to tell you how to, it's a part 2 of this video, and it will show you how to apply that to using z-scores a little bit more in depth.